Welcome to Julia for Talented Amateurs, where I make wholesome Julia tutorials for talented amateurs everywhere. I am your host, the Dabbling Doggo.
I dabble.
Last week, we got an overview of analysis. After that, we looked at some real-world business applications. Along the way, we added to our visualization toolkit by learning how to use Kairomaki. Today, we'll learn how to solve optimization problems by using the JUMP package. We'll continue to add to our visualization toolkit by learning how to use the Plotly.js backend to the plots package. According to Wikipedia, mathematical optimization, or mathematical programming, is the selection of a best element from some set of available alternatives. In the simplest case, an optimization problem consists of maximizing or minimizing a real function by systematically choosing input values from within an allowed set and computing the value of the function. As a field of study, optimization has been around for a long time, well before computers. A lot of business issues are just optimization problems, so it's used a lot in the business world. Of all of the analytic tools that you will learn in this tutorial series, optimization is one of the most practical tools to have in your toolkit. According to their GitHub page, JUMP is a modeling language for mathematical optimization. It was started in the 2012 to 2013 timeframe by Ian Dunning, Joey Hudgett, and Miles Lubin, who were all PhD candidates at MIT at the time. I'm not sure who should get top billing here, so I've listed their names in alphabetical order. For reference, 2012 was the year that Julia released version 0.0.0. JUMP stands for Julia for Mathematical Programming. Here, programming doesn't refer to computer programming. Rather, mathematical programming is another term for optimization. The JUMP package itself is not an optimization model. Instead, JUMP is a language written in Julia that allows a user to use a common syntax to access many different optimization solvers. These solvers are a combination of commercial and open source solvers written in various programming languages. Today, JUMP is one of the largest, most established packages available in the Julia ecosystem. It currently supports 24 different solvers and has a large developer and user community. They even have an annual developers conference, like a mini JuliaCon. To give you a sense of how massive this project is, they've been working on JUMP for almost 10 years, and they still have not released version 1.0 yet. This is the type of package that large institutions would be willing to pay a lot of money for, and yet the developers of JUMP have generously made it available for free to the public, so that average citizens, like you and me, can participate on a level playing field with the likes of big businesses, governments, research universities, and the military. In today's tutorial, we'll be using two different solvers along with the JUMP package. glpk.jl is a Julia wrapper for the GNU Linear Programming Kit library. According to Wikipedia, linear programming is a method to achieve the best outcome in a mathematical model whose requirements are represented by linear relationships. Also according to Wikipedia, GNU is an extensive collection of free software. So, GLPK is an open-source GNU linear optimization solver. glpk.jl just makes that open-source code available within the Julia programming language. The other solver package that we'll be using is ipopt.jl. ipopt.jl is a Julia interface to the CoinOR nonlinear solver called ipopt. ipopt stands for Interior Point Optimizer, and unlike GLPK, ipopt is used to solve nonlinear problems. CoinOR stands for Computational Infrastructure for Operations Research. It was founded in the year 2000 by a group of IBM researchers who proposed open source as a means to publish software, models, and data. It is operating today as an educational nonprofit foundation. As you can see, both GLPK and ipopt are solvers that exist outside of Julia. In the past, if you wanted to access them, you would have to learn a different syntax for each of them, in addition to learning Python and C++. With JUMP, you can do everything in Julia and use a common syntax for any solver supported by JUMP. I know this may sound a little abstract at this point, but it will become clear as we go through the examples. We're also going to add a package called plots.jl, as well as a package called plotlyjs.jl. Conceptually, the plots package is similar to the JUMP package, in that the plots package, despite its name, is not actually a plotting package. Instead, the plots package is a high-level interface that serves as a plotting front end that can access several different plotting packages to use as backends. The plots package was created by Tom Breloff. In addition to supporting Plotly.js, the plots package also supports the use of GR and PyPlot as backends. Plotly.js.jl is the Julia interface to Plotly.js. Plotly is a for-profit Canadian company that is behind Plotly.js, which is their open-source charting library written in JavaScript. Okay, enough with the backstories. Let's get into VS Code and have some fun. Open VS Code. Click in the terminal and hit Alt-J and then Alt-O to start the REPL. Maximize the REPL by clicking on the up arrow. Enter the close bracket to enter the package REPL. In the package REPL, add the jump package version 0.21.5. Note that jump is spelled with uppercase JMP and a lowercase u. Hopefully you got an error. Last week, I mentioned that sometimes Julia doesn't load the latest version of a package. Oftentimes, that's because there's a conflict with some other package that you've already installed. The solution to this is actually quite simple, but it's not obvious. Julia recommends that you set up a new programming environment every time you start a new project. This means setting up a new working directory and then adding any package that you will be using for that project into that new directory. Here's how to do that. Exit the package REPL by hitting backspace. In the Julia REPL, view your present working directory by using the pwd function. This is the location where all of your files are currently being saved to. Create a new directory called tutorial02by03 by using the makeDirectory function. Change your working directory by using the changeDirectory function. Enter pwd again to confirm that your working directory has changed. Go back into the package REPL by hitting the close bracket. In the package REPL, type in activate, followed by a blank space, then followed by a period, and hit enter. Notice that the prompt has changed. Now try to add the jump package again. It should work now. Go ahead and load the other packages that we'll be using for this tutorial. Type in status to confirm that your packages have been added with the correct versions. Notice that none of your other packages from the previous tutorials are showing. Exit the package REPL by hitting backspace. In VS Code, click on the Explorer icon to open the Explorer. Notice that there's a new folder called tutorial02by03. If you click on it, it reveals that there are two files, manifest.toml and project.toml. These are the files that keep track of the Julia package versions that are being used in this project folder. Minimize the REPL by clicking on the down arrow. If you haven't done so already, create a new file by going to File, New File. Save the file as tutorial02by03.jl by going to File, Save As. Before saving, confirm that this file is being saved to your new directory. In the Explorer panel, notice that your file shows up in the new directory. Close the Explorer panel by re-clicking the Explorer icon. We're going to need to see more of the REPL today, so let's reconfigure the VS Code user interface. Right-click along the top bar of the terminal panel and select Move Panel Right. Add the Plots panel by going to View Command Palette. Move the Plots panel so that it's sitting behind the editor. Adjust the REPL panel to make it wider. Adjust the Workspace panel to make it smaller. Click in the editor. I'm going to add a header with some comments. There's no need for you to type this in. All of the files used in my tutorial will be saved to my GitHub repository. The link is in the description below. The best way to learn how to use the jump package is to just go through some examples. There's a package called jumptutorials.jl that's a good place to start. This first example comes directly from their Getting Started with Jump tutorial. This is how an optimization problem is presented in math. You can interpret this notation as find the minimum value of 12x plus 20y, subject to the following constraints. In school, students would be expected to solve this by hand. Let's see how we would solve this using JMP. The first step is to select the packages. Select both rows and hit Shift-Enter. As I mentioned earlier, GLPK is the solver for linear optimization problems. It will become clear what that means as we go through the examples. For now, let's just enter the code as it's presented in the tutorial. Select the row and hit Shift-Enter. 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 It looks like we got the same answers as in the tutorial, which is a good sign. However, you might be wondering, when in the world am I ever going to need this? Why would I ever need to find the minimum value of 12x plus 20y? As it turns out, optimization is used a lot in the real world. However, because this example is so abstract, it's difficult to see the usefulness of it. In order to help make these problems more understandable, optimization problems are often presented in the form of a word problem, with a couple of sentences that describe the situation that you're trying to solve. So I'll do that with the rest of my examples. The other thing that this example illustrates is that the workflow for solving optimization problems is pretty well defined. Let's add a workflow template to our file so we can copy and paste it for the rest of our examples. Now that we have a workflow established, let's move on to our next two examples. The knapsack problem is like the hello world for optimization problems. To reinforce just how long folks have been studying optimization, work on the knapsack problem can be traced back to as far as 1897. The objective is to package the most valuable items without overloading the luggage. There are two different versions of this problem. The first version assumes that there's only one box of each item available, so the choice is binary, either you take it or you don't. The second version assumes an infinite supply of each box, so you can take as many boxes as you like as long as it fits in your luggage. To me, the answers are not obvious just by looking at this diagram. Let's see how we can use JMP to solve this problem. Select the steps in the workflow template and hit Ctrl-C to copy. Select the blank line below the title and hit Ctrl-V to paste. Enter a description under Describe Situation. Under Select Packages, select JMP and GLPK. There's no need to select the packages again, so you can toggle the comments on by selecting the rows and hitting Ctrl//. Under Select Model, select the GLPK optimizer. Select the row and hit Shift-Enter. Under Define Variables, set up a variable for each box. Bin is short for binary. This tells JMP to return either 0 or 1. Note that these are all macros. Select all of the rows and hit Shift-Enter. Under Define Constraints, add a brief description and then enter in the constraints for the total weight function. Select the rows and hit Shift-Enter. Under Set Objective, add a brief description, and then enter in that you want to maximize the total dollar function. Select the rows and hit Shift-Enter. Under Run Solver, enter the Optimize Bang function. Select the row and hit Shift-Enter. Note that the Optimize Bang function finds a solution for you, but it doesn't display anything. Instead, it stores the results in memory, so if you want to see the results, you have to ask for it. Under Display Results, set up the different colored boxes as a vector, and then create a for loop to display the results. Select the rows and hit Shift-Enter. Display the value for total weight. Select the row and hit Shift-Enter. Display the value for the maximum total dollar value. Select the row and hit Shift-Enter. So, according to this optimization model, we should take every box except for the green box. That will give us a maximum dollar value of $15. Put that under the Conclusions section. Pretty cool, right? Now, let's take a look at what happens if we assume an infinite supply of boxes. Go back up and copy the code for example 2, and then paste it down below. Change example 2 to example 3. Change binary to infinite supply. Under Describe Situation, change the second sentence to assume an infinite supply of boxes for each color available. Under Select Packages, there's no need to change this section. Under Select Model, even though we're using the same GLPK model, we still need to enter this line again. Calling the model function will reset the model, so the model can be used to solve a new problem. Select the row and hit Shift-Enter. Under Define Variables, add a greater than or equal to 0 after each color. Change bin to int, int. Change binary to integer. Now select all of the variable rows and hit Shift-Enter. Under Define Constraints, there's no need to change these constraints, since we're still constrained by the same total weight limit. Select the constraint rows and hit Shift-Enter. Same thing for the objective. There's no need to change the objective, since our objective is still to maximize the total dollar value. Select the objective rows and hit Shift-Enter. Now select the optimized row and hit Shift-Enter. To display the results, select the rows and hit Shift-Enter. Notice that the results have changed. If there's an infinite supply of boxes, then we should grab 3 yellow boxes and 3 gray boxes. Select the value row and hit Shift-Enter. Notice that the total weight has changed from 8 kilograms to 15 kilograms. It's heavier now, but is still within the weight limit. Select the objective row and hit Shift-Enter. Notice that the dollar value has changed from $15 to $36. By allowing for an infinite supply, we've more than doubled the dollar value. Change the conclusion to reflect all of the changes. Easy, right? So far, all of the examples were linear optimization problems, meaning that the objective function that we are trying to minimize or maximize could be expressed as a straight line. However, if your objective function is curved, for example an exponential function, then this is an example of a non-linear optimization problem, and you'll need to use a different solver. For non-linear optimization problems, we're going to use the IPOpt solver. The workflow is the same, but the macro for constraint and objective will have an uppercase NL in front of it to indicate a non-linear constraint and non-linear objective. Copy the workflow template and paste it here. In this example, you're a farmer who owns some sheep. There's a stone wall in your field, and you want to build a rectangular, fenced-in yard along this wall to hold your sheep. You have 100 feet of total fencing material. What dimensions should you use to maximize the area of the yard for your sheep? Under Select Packages, select IPOpt. Select the IPOpt row and hit Shift-Enter. Under Select Model, select the IPOpt Optimizer. Select the row and hit Shift-Enter. Under Define Variables, set up the variables x and y to represent the sides of the rectangle. For non-linear optimization problems, you need to select a starting point. The non-linear solver will go through several iterations as it tries to find the optimal solution, but it needs a starting point before it can begin. Select both rows and hit Shift-Enter. Under Define Constraints, enter the function for the total length of the fencing material. Use @NL_constraint instead of @constraint. Select the row and hit Shift-Enter. Under Set Objective, enter the function for the area of the rectangle. Use @NLObjective instead of @objective. Select the row and hit Shift-Enter. Under Run Solver, use the Optimize Bank function just like before. Select the row and hit Shift-Enter. Notice that there's a lot more going on in the REPL with the IPOpt solver. The solver is going through several iterations in order to find the optimal solution. Just like with the linear solver, this non-linear solver saves the solution in memory, so if you want to see the results, you need to ask for it. Select the row and hit Shift-Enter. Select the row and hit Shift-Enter. Select the row and hit Shift-Enter. So, in order to maximize the area, you need to build a yard that is 25 by 50. Add a description under the Report Conclusion section. Does that surprise you? Why doesn't a square yard have the maximum area? It might be helpful to have a visualization of the objective function to see what the solver is looking at. Let's use the plots package along with the Plotly.js backend for this visualization. Note that Plotly.js is all in lowercase. This indicates to the plots package that you want to use Plotly.js as the backend. Select both rows and hit Shift-Enter. You may need to adjust those resolution numbers to match the resolution of your monitor. Those are the settings for my monitor. Select the range for the x-axis. Select the row and hit Shift-Enter. Set up the objective function for area as a function of x. Since we know that x plus 2y equals 100, we can calculate that y equals 100 minus x divided by 2. Select the row and hit Shift-Enter. Now, generate the plot. As you can see, this syntax is a lot simpler than the syntax we use for Mach-E. Select the rows and hit Shift-Enter. The plot should appear in the Plots panel. Plotly has a nice interactive user interface. As you hover along the curve, the plot displays the values for x and y. In addition, there are some useful icons in the upper right corner. Most of them are self-explanatory. Skip the camera icon for now. I'm going to show you a different way to save this plot. I'll click through the icons quickly, but definitely play around with it if this is your first time using Plotly.js. As you can see, the area function is not a straight line. This is a typical example of a non-linear objective function that requires the use of a non-linear solver like iptopt. On the plot, it's easy to see that the maximum area is reached when x equals 50. When x equals 33, that's when the yard is a square. As you can see, the area of that square is less than optimal. Go back to the editor and save your plot. You can save it as an SVG file. Select the row and hit Shift-Enter. Go into your folder and open your SVG file in your browser to confirm that it's saved. Zoom in as necessary. Unfortunately, the SVG file is a static image, so it's no longer interactive. Generating visualizations using the Plots package is a lot easier to do compared to Maki. Plotly.js also has some very nice interactive features. For these reasons, using Plots and Plotly.js is a great choice for day-to-day work-in-progress visualizations. However, the presentation quality of the plots is less than ideal, so, in my opinion, Plots and Plotly.js are best suited for mid-stage analysis, when you need the functionality, but you're not really concerned about the presentation yet. Let's take a look at another non-linear example, this time trying to find the minimum value. Go ahead and copy and paste the workflow template here. In this example, there's a race that involves running east along a beach and then swimming north to an island. Measuring along the beach, a racer would have to run 6 miles to be directly south of the island. The island is 2 miles north of that point on the beach. The racer can run 8 miles per hour and can swim 3 miles per hour. The racer is allowed to enter the water at any point on the beach to begin swimming to the island. At what point should the racer enter the water in order to minimize the total travel time to the island? A naive guess would be to run all 6 miles east along the beach and then make a sharp turn north and swim 2 miles to the island. However, is there a different point along the beach where the racer should enter the water and swim to the island in order to minimize the total time? Let's see how to solve this using Jump. As always, select the packages first. Since we're already using these packages in our current session, you can comment this section out by using Ctrl//. Since this is a non-linear problem, select the iptopt solver. We need to reset our model, so select the row and hit Shift-Enter. Let's define the variable. In this case, we want to find the distance from the start line, where the racer should enter the water along the beach. The total distance along the beach to the island is 6 miles, so x should be somewhere between 0 and 6 inclusive. Select the row and hit Shift-Enter. Under the Define Constraint section, there are no other constraints in this case, so just enter #none so you know you didn't skip this step by accident. For the objective function, we're going to need to do some geometry. If the racer enters the water from some random point along the beach, then we need to know the distance from that point to the island. That distance is the log side of a right triangle. From the Pythagorean theorem, we know that a squared plus b squared equals c squared. Using this, we know how to calculate that distance as a function of x. Since we're trying to solve for the minimum time, we need to divide our distance measurements by the racer's speed in miles per hour. This will give us a function for the total hours with respect to the distance x. Let's use that function as our objective function. Note that we need to use NL before objective because this is a nonlinear objective. Select the row and hit Shift-Enter. Under Run Solver, enter the Optimize Bank function. Select the row and hit Shift-Enter. Now display the results. There's only one variable in this example. Select the row and hit Shift-Enter. To see the objective value, select the row and hit Shift-Enter. So it looks like the racer can save time by running most of the way along the beach, but entering the water around the 5.2 mile mark. Let's report our findings and the conclusions. This solution may not be obvious, so let's visualize it to see what the solver is looking at. Since we've already done this in our session, you can comment these lines out. Let's set up the x-axis from 0 to 6 to reflect the 6 miles along the beach. Select the row and hit Shift-Enter. Next, set up the objective function time as a function of the distance x. Select the row and hit Shift-Enter. Now generate the plot. Select the rows and hit Shift-Enter. Your plot should appear in the Plots panel. You can see that the time function is a curve, but it's not obvious by looking at the plot where the minimum value is. Toggle on the spike lines and hover your cursor along the curve. Start at x equals 0 and try to find the minimum manually. Select the zoom icon and click and drag the bottom of the curve to get a better view and try to find the minimum again. Click on the home icon to reset the plot. While it's possible to estimate the solution by looking at a plot, in this case, you need a more sophisticated optimization tool to find the precise answer. Go back to the editor and save your plot. Select the row and hit Shift-Enter. View your plot in the browser to confirm that it's saved. Our final example is another nonlinear problem, which illustrates how optimization is used in business. Last week, we saw supply and demand curves that show the relationship between price and quantity as it pertains to the behaviors of companies and consumers. Companies use that information to create revenue curves, which is just the price times the quantity. Companies use optimization to identify the price that gives them the maximum revenue. Actually, companies are looking for the maximum profit, which is a slightly different calculation. But for demonstration purposes, let's assume that the maximum revenue also generates the maximum profit. In this example, a car rental company is trying to set the price for the daily rental rates for their cars in order to maximize their revenue. They can charge anywhere from $50 to $200 per day, and they have calculated a demand curve for their cars, which is Q of P is equal to 1000 minus 5P. Go ahead and copy and paste the workflow template here. Describe the situation. Select the packages. You can comment these out by selecting the rows and hitting Ctrl//. Select the solver you want to use. We'll be using IP-opt again. Select the row and hit Shift-Enter. The variable in this case is P for price, which is a number between 50 and 200. Tell your model to start guessing at 50 and not 0. Select the row and hit Shift-Enter. There are no other constraints in this example, so enter #none. The objective function is the revenue function, which is price times quantity. We can use the demand curve function to plug in as our quantity. Select the row and hit Shift-Enter. Run the solver. Select the row and hit Shift-Enter. Now display your results. Select the row and hit Shift-Enter. Select the row and hit Shift-Enter. Is this answer surprising to you? A naive guess would be that in order to maximize your revenue, you should charge the maximum price of $200. According to this model, your maximum revenue is achieved at $100, not $200. Report that in your conclusion. In order to better understand why the maximum price doesn't deliver the maximum revenue, it would be helpful to visualize it. You can comment those lines out since we've already done that. Let's plot price along the x-axis from 50 to 200. Select the row and hit Shift-Enter. Next, set up the objective function revenue as a function of the price P. Select the row and hit Shift-Enter. Now, generate the plot. Select the rows and hit Shift-Enter. Click on the Plots tab to view your plot. Toggle on the spike lines and hover your cursor over the line starting at 50. As you can see, the revenue initially increases as you raise your price, but at some point, your revenue begins to fall as customers lose interest in your service because the price is too high. In fact, if you charge the highest price of $200, your revenue would be zero since no one would be interested in renting from you at that price. After seeing this plot, it's easy to understand why companies are interested in optimization models. Go back to your editor and save the plot. Select the row and hit Shift-Enter. View your plot in your browser to confirm that it's saved. Just for fun, let's take a look at the demand curve. Select the row and hit Shift-Enter. Now enter the code to generate the plot. Select the rows and hit Shift-Enter. Click on the Plots panel to see your plot. Toggle the spike lines on and hover over the curve starting at 50. You can see the demand fall to zero at $200, but it's not immediately clear where the revenue maximizing point is just by looking at the demand curve. In fact, you might be tempted to charge the lowest price since you could rent out the most cars. You'll see companies do this all the time. They'll charge the lowest price so they can get the highest market share, but as a result, their profit margins are really low. If you've ever wondered why some companies charge a slightly higher price and accept a lower market share versus their competition, this is why. They've figured out that they can actually make more money by selling fewer products. Click on the back arrow to take you back to the maximized revenue curve. It's obviously much easier to make pricing decisions by looking at the revenue curve versus the demand curve. Go back to the editor and save the demand curve plot. Select the row and hit Shift-Enter. Open your plot in your browser to confirm that it's saved. Being able to solve optimization problems is one of the most practical skills that you can develop. Optimization problems occur everywhere in our daily lives. Companies aren't looking for mediocre performance. They're looking for maximum profit and minimum cost. They want maximum quality and minimum downtime. They want maximum customer satisfaction and minimum product returns. All of these are examples of optimization problems. Learning to recognize optimization problems is a large part of the process. From our examples, you know that it takes longer to describe the problem than it takes to actually solve the problem. Being able to verbalize the problem is critical to understanding which model you need to use and how to set up that model. Once that's done, solving the problem becomes trivial. When possible, it is often helpful to visualize the objective function, since optimization problems are often counterintuitive. Having JMP in your analysis toolkit is invaluable, since it provides a common language for you to access some of the world's best solvers for free. Well, that's it. Today, we learned about optimization. We added the JMP package along with a linear solver and a non-linear solver. In addition to adding to our analytic toolkit, we added to our visualization toolkit by adding the plots package and the Plotly.js plotting package. Next week, we'll dive into the subject of statistics in Julia. If you enjoyed this video and you feel like you learned something new, please give it a thumbs up. For more wholesome Julia tutorials, please be sure to subscribe and hit that bell. New tutorials are posted on Sundays. If you have any questions, please post them in the comments below. Please feel free to share these videos since these tutorials are getting rave reviews. Just listen to what the professional reviewers are saying.
Satisfaction score, 10 out of 10.